Yesterday, we ended with the second type of the cooling crystallizers. So we have the agitated vessels. So actually, under the cooling crystallizers, we have 4. So we have covered already the 2. And for today, we'll be discussing the third of the 4 under the cooling crystallizers. So the third type is the scraped surface crystallizers, and these are the Swenson-Walker scraped surface units, which are used for processing in organic salts. Now, these have high temperature solubility coefficient with water. Now, this particular type of crystallizer units are semi-cylindrical. So it could be something like you view it as a cylinder and you cut it in half, and it is in a form of a straw, about 6 mm wide and 3 to 11 meters long. So these semi-cylindrical straw are filled with water-cooled jacket. So this is where the cooling medium, of course, enables the shall I say, the magma, the mixture of the mother liquor and the crystal to cool down, and as such induce the growth of crystals. Now, it has a helical scraper rotating at 0.8 to 1.6 hertz, which keeps the cooling surfaces clean and enhances growth of crystals by moving them through the solution, which is slightly sloping downwards. So the movement of the mixture of your mother liquor and crystal, which would later be on separated, is by virtue of gravity. Now, they are used also to processing fats, waxes, and other organic melts. Now, this one is a fully closed Swenson-Walker crystallizer, cylindrical also in shape. That the one that the original design actually is an open type semi-cylindrical straw. Both of this one is enclosed, while the other one that is being described is semi-cylindrical, has a helical screw rotating. That way, in the movement of the screw, the magma already is dispensed downwards by virtue of gravity as the screw moves forward. Now, we have here a sample problem application on the Swenson-Walker crystallizer. And this particular crystallizer is used to process a solution containing 23% by mass of sodium phosphate, which is being cooled from 313 to 298 Kelvin. Now, the cooling is used to form the crystals of sodium phosphate, dodecahydrate. I'm not sure if 12 is alright. If we have dodeca, I'm not so sure about 12, but it is already hydrated in this form. Now, the solubility of your sodium phosphate at 298 is 15.5 kilograms per 100 kilogram water. And the required product rate of crystals is 0.063 kilograms per second. Now, the mean heat capacity of the solution is 3.2 kilojoule per kilogram degree Kelvin, and the heat of crystallization is 146.5 kilojoule per kilogram. If cooling water enters and leaves at 288 and 293 respectively, and the overall heat transfer coefficient is 140 watt per square meter degree Kelvin, you are asked to determine what length of crystallizer is required, assuming area available is 1 square meter for every 1 meter length of pipe. Okay, somebody wrote in the chat box, wala naman nag-change ang slide. It's okay. So I will just not project this one. We'll just increase the can you see it now? Well, I have to share again. Can you see the unprojected slide, the one in pink?
Yes, ma'am.
Okay. I'm not sure what's going on with this particular PowerPoint slide. So this is the problem that we need to work on for now, a sample problem on our Swenson-Walker crystallizer. So let me go to the Jamboard and write down our given information. Okay, let me just use a different one, new one. Can you see the Jamboard? Do you see the Jamboard? Okay. So this is our, if I'm not mistaken, is this the fourth sample problem already? Let me check. Okay, this is our fourth sample problem already on this topic. So I'll give you the given based on what was read to you. So our crystallizer is a Swenson-Walker crystallizer, and it's using water cooling jackets. Okay, we will assume that the manner of contact of our cooling medium and our feed to our crystallizer is countercurrent, though it's not mentioned in the problem, since we know that countercurrent design is much more efficient than the co-current design. So this is countercurrent. We'll have, of course, sorry. There must be some degree of evaporation here, but if it's not mentioned in the problem, then we will not account for it. So this is the B, but this is how we illustrate completely our crystallizer. So we have the feed here. We have the magma. And we have the liquor. We have here the crystals. Okay. Now, as to the given, we are to process 23%. By weight, sodium phosphate. And the temperature of the feed is given at 313 Kelvin. Now, as to our crystallizer design, the initial water here, I like to label as T1, is at a temperature of 288 Kelvin. The final temperature is 293. Okay. And then it's being mentioned that the heat of crystallization, I'd like to write it here, is 146.5 kilojoule per kilogram. And then we have the overall heat transfer coefficient that is provided as well, 140 watt per square meter per Kelvin. Now the solubility that is given, so meaning that's the final concentration, I'd like to place it here, whatever is the concentration inside, that would be the concentration that is being dispensed also outside. This is 15.5 kilograms per 100 kilogram water. Now our crystals is in this form already, in this hydrated form already. Oh, this is 12, not 10. And this is the rate of crystal removal. So it's 0.063 kilograms per second. So this is the rate of crystal removal. So I think we've covered everything here. By the way, the CP, the heat capacity, is 3.2 kilojoule per kilogram Kelvin. Hi, so everything is in here already. So this is our given information, and we are to determine. So this is now more on crystallizer design, because we're talking of the types of crystallizers already. So it's asking for the lengths, how many lengths of pipe will we use if you have available 1 square meter of area for every meter length of pipe. So we're going to buy pipes which has this heat transfer area available for every meter length. So 1 square meter. So how many lengths would that be then in our case? So we'll proceed to the solution of this problem. And though the previous concentrations or the previous problems that we have discussed are all concentrated on the use of the material balance, because it's been asking about yield and anything associated with the yield, this one now has its concentration more on the design. And if we are to think of a formula that is made available for us that will lead us to the required information, so this is the required information, the lengths of cylindrical pipes that will be used for this Swenson-Walker crystallizer, you have to think of a formula that you already know in the past, because in here, especially in this type of Swenson-Walker crystallizer, there's no specific design equation available, but rather from the previously learned principle you have regarding heat transfer, what particular formula is it that you have already or that you can recall that will lead you to not exactly make you solve right away the lengths of pipes, but rather would lead you to the lengths of pipes that you would be needing for this particular crystallizer that you are to design. So think of a unit, rather think of a formula that you know already regarding heat transfer that would lead you to the required information, which is the length of pipe. What do you think is that formula? Because in here we don't have a specific formula for Swenson-Walker to use regarding design. So we go back to the fundamentals again of heat transfer. Now, what formula do you think would that be? Do you have any idea what heat transfer formula will you use that can lead you to the lengths that you will be using here? So these are your given information. So I'm asking if anybody has an idea for that formula that you will be using. So actually, this is one hybrid problem again in unit operations. So though we're talking about crystallization, but you're using less principles learned in heat transfer, we were done with it, and principles learned in design of heat transfer equipments. So no particular formula in this case. So somebody wrote here. Okay, there's a suggestion that we will use QA dt dx. If it's QA dt dx, what's the limitation of this particular formula? You're suggesting that we're going to use Fourier's law. What's the limitation of this? The limitation of this suggested formula is that you have a heat transfer that is one directional only, perpendicular to the surface. So specifically, this is applicable to conductive heat transfer. In the case of heat transfer in Swenson-Walker type of crystallizer, it's from the center emanating outwards. So the direction of heat transfer is radial coming from the center. So then we cannot use Fourier's law in this case. Okay, so there is a suggestion that we use the UA delta T. Very good. So you will use, in this case, the formula UA delta T log mean. Now, in particular, very good. In particular, you will use this one primarily because you will capitalize on the delta T. You will capitalize on the A here. This is where you're going to capitalize on. If you have the area already determined, then you can know the lengths of pipes that you will be using based on the available pipes to be bought from suppliers. That is. So we need to determine the area. That way we can determine the lengths of our pipe. So let's say this is our equation 1. For us to be able to know this area, then we need to know the Q, the U has to be given in the problem, and the delta T log mean that is. Why did I only write the T? It's very hard class to write, especially you're explaining at the same time in here, delta T log mean. Hi, that's it. Now, going back to what I'm saying, you need to know the Q, you need the U has to be given, and the delta log mean has to be solved as well. Now, in the case of crystallization, I like to use a different color here. The Q here will constitute for the Q for cooling because we're talking of a Swenson-Walker crystallizer, and the Q for crystallization. So it's not just using the Q for crystallization like in the problems that we have solved previously, the first 4 sample problems wherein we only use the Q for crystallization. In here, we need also to determine the Q for cooling because our Swenson-Walker crystallizer needs this particular amount of heat to cool down the magma inside it so that crystallization will also proceed. So we need to account for this too. Now, for the delta T log mean, this one, I already mentioned when I was writing the given that we will assume counter current flow. Okay? Now, this one is already given as it is. It's already known and it's written in our given information. So based on the 2 informations left for us to determine that way we can get the A from this equation, I think the delta T log mean is easier to determine at this point. So we have a delta T log mean, and we have its formula as well discussed in heat transfer, in our topic on heat transfer. So in here, if it's a counter current flow, we have delta T1 minus delta T2 divided by the ln of delta T1 over delta T2. Now, if you're going to look at delta T1, I'd like to go back on the given. That way you can pinpoint to me what's the delta T1. I saw arranged already the way I have drawn here your crystallizer, the feed, and the cooling water direction. That way you will know what's the delta T1 and what's the delta T2. Now, based on what you have learned in heat transfer, this would be our, here is our delta T1. In here, we have our delta T2. Okay? Now then, we can go to our formula for delta T log mean. So by the way, did I write all the temperatures that I'm supposed to write? Did I miss something here? The final temperature, let me go back to the problem class. I'll project to you the slide. So a solution which is 23% is to be cooled from 313 to 298. So did I place it there correctly? Let me check. So 313 to 298. Okay, so I did not place the 298 here. So that is why I was wondering why I didn't have any temperature. So the process of cooling, I'll place the temperature here in the crystallizer because it's the same temperature that will be dispensed for your magma. 298. I missed to write the 298 here. So the T sub, so I use already T1 and T2 here. I use TF for the feed. Then I'll place here T sub F. That's for the magma. The solution comprising already of your liquor and crystals when separated. So I'll place here 298 Kelvin. Okay, so you would know what your delta T1 and delta T2 is based on this illustration. So if we go back to our formula, this is our formula already. Your delta T1 is 313, the temperature of our feed, minus 293, the temperature of the cooling water leaving the coils. And then we have our delta T2, the final temperature of the magma, and then we have this one as the initial temperature of your cooling water, the 288. So in here, you will have the ln of these same expressions that we have on top. So giving you a delta T log mean, just check my values class, that would be 14.43 degree Kelvin. Okay, now with this, we know already the delta T log mean in here. Now the next thing that we are to determine is the Q for cooling and the Q for crystallization. So let's go to the next page. Now, if we will determine the Q for crystallization, we will use the one that is given in the problem. However, we are to make use of the actual rate of production of crystals once they are separated already from the liquor. So in the case of Q for crystallization, you will use the amount of crystals produced and the Q that is given, the Q for crystallization. That way, your unit would be in kilowatt. Now, because we're talking about Q. Now, in this case, you have 0.063 kilograms per second, as stated a while ago as the rate of crystal production. And we multiply it with the heat for crystallization. Now, you will know for 1 plus that there's a need for you to multiply your heat of crystallization given to the actual amount of crystals processed. It's because your unit here is kilojoule per kilogram. We want a unit for our heat transfer, as in the rate of heat transfer, and that's in watt or in kilowatt. So in this case, you can cancel now the kilogram unit, giving you a Q of crystallization, which is 9.23 kilowatt. Okay. So by the way, we already determined this one. From the unknowns that we have written here, we're already good with this. Okay. Now, next is the Q for crystallization. Sorry. We're already done with the Q for crystallization, and after this, we will determine the Q for cooling. So this is the next one. Now, the Q for cooling, what do you think will be the Q for cooling based on the information that we have, that I have written here? So I'll go back to the given. That way, you can work your way through the information that is provided by the problem. If it's Q for cooling, that would be needing the what? What do you need to cool down? You need to cool down the what? Q for cooling. What do you need to cool down? You may write on the chat box. You need to cool down the, in the first place, what is to be processed by this crystallizer? It needs to be cooled down before the crystal starts to be formed and grow. Correct. It should be the feed. So I start with that. I write a formula that will account for the degree of cooling of my feed because it's the feed that you're going to cool down. So I'll write the feed. What do you think? Lesson again in the past that you will place in here. That way you can account for a simple process of cooling. What formula would that be? A general formula for heat transfer, whether it's cooling or heating. What is that? We account for the amount of heat transferred. So MCP delta T. So in this case, now we use, very good, FCP delta T. Okay, now let's check in this formula if everything is known already. Again, because we solved this problem backwards. As to the given information, I have already the CP, and I have the corresponding change in the temperature of my feed, original and final temperature. Excuse class, ha? Sorry about that class, ha? Budlay maging nanay kay pangayuan kapag face mask if they are leaving the house. Anyway, so where was I? So I said we have already the feed, and then we have the CP, and we have the delta T of the feed, all in this representation, but we don't know the feed yet. It's not given here as to what is the feed, but we know that it's 20% by weight sodium phosphate. So I will go back to our formula and then write down what we know. We have this and we have this. Now, we do not know the feed yet because it's not given there. The actual amount is not given. So for now, I'll have this as our equation 2. Now, I will ask you again another question going back to our given. So this is our set of given information. What should be then a manner, or what should then be the route that we should take? That way we get to know this feed. So based on the given information that is written here, where can I get the feed in this case? Or what would lead me to the actual feed that was processed by my crystallizer? Where will I get the F based on the provided information here? And the fundamentals that we have discussed in the first 4 or in the first 3 examples that we have covered. So there's an answer here. So we will be needing overall solid balance. Okay, we will do overall solid balance, and if we will use it, what's the simplest way that will account for the solids present in our feed, at the same time the solid that is present, or the solids that are present in our crystals? I'm giving already the hint there. I will find the feed based on the rate of the production of my crystals. So how will I write it in terms of what you have learned in the first 2 examples? I will account for the feed based on the crystals. So there's a suggestion here. FXF is equal to XCX. Now, do we have the solid content of our feed? The answer is yes. Do we have the solid content of our crystals? The answer is, we know the actual crystals, right? But we don't know the actual X sub C that we're going to substitute to it. Okay, to shorten the discussion, you need to link your feed to the rate of crystals produced. What particular information will you use to link the two? Okay, I'll write it here. So I'll read what is on the yield. Very good, John. You will connect the feed to your crystals based on the yield. Now, based on that particular suggestion, what do you think is the very simple formula that you will use? That way, you may be able to connect the feed to the crystals using the yield. What would be that very simple formula? Okay, somebody wrote in the chat box, C is equal to the feed times the yield. Very good. So see, you don't use any particular new formula here. You simply use of what's available in the problem, the information that is available in the problem. So in this case, we write a third formula, the C equal to the feed times the yield. Now, this formula again, if you look again closely to this particular formula, you have the C because the problem gave you that one already. You want to know the feed, that way you can substitute it in here so you can determine the cooling. But do you know the yield? For now, do you know the yield? The answer is not yet. You do not know the yield. Both of these information are unknown. You need to know the yield, that way you get to know the feed. If you know the feed, you substitute in here, you know the cooling. So then the next step for us is to determine the yield. So this would be another equation that you will label for now because you do not know yet what is the yield. Okay, now we will go to the yield. For the yield, of course, you know already the formula because we have discussed it in the first three examples. So what is the formula? If you can memorize, what's the formula for the yield? Yield is equal to, correct me if I'm wrong, R omega 1. And you have here C sub 1 minus C sub 2 times 1 minus E. And then we have 1 minus C sub 2. You have R minus 1. So this is the formula of the yield that we have been using, already derived from the solid balance and the solvent balance for our material balance equations. So I can check whether what I know here is already provided, then I can make my way through the yield. So let's see. What do we know? So we have the concentration. We don't know yet the concentrations that should be written in that particular formula. So this should be anhydrate over solvent. And we know that there was no mention about cooling in the problem. I'd like to share again the slide. I don't happen to recall there is a mention of water evaporated here. The unit only made use of cooling. So there was no water evaporated. So it's okay, class, to set it to 0. So I'll go back to our board and set our E to 0. So everything here, we need to determine, right? So we need to determine first the R, W, C1, and C2, whichever you want to do first. So this will be our fourth equation. I need first to determine the R. So for the R, you have the anhydrate. Oh, sorry. For the R, we have the hydrated form. Okay, so we have molecular weight. And we have here the anhydrous. Okay. Let me check if I have already the info here. So please check if my molecular weights are correct. So you have here 380 for the R, and for the sodium phosphate alone, you have 164. So you'll be getting here 2.32. Now, for the C sub 1, you need to determine it based on the percentage solids given in the problem. So C sub 1 then is 23, the solids over the water. So this is how we express the concentrations when we solve based on that particular formula of the yield. So your answer here is 0.2987. So kilogram solute, kilogram water. Now your C sub 2 is given as well, but it should be expressed clearly as one value. So 15.5 of the solids per 100 kilogram of water. So this is 0.155 kilogram solids again over kilogram water. Now, next would be the omega 1, the water content of your feed. So in this case, since we have 23% solid, so your amount of water is 0.77. So for every 1 kilo of feed that we process, we have 0.77 kilogram of that containing water. Now, we go to our equation for the yield here and substitute. So I will simply place here substitute to equation 4. So y then would be equal to 2.32 times 0.77. We have here 0.2987 minus 0.155. Since I already placed here that your E is 1, so we have that only in the numerator. And my denominator will be simply 1 minus C2, R minus 1. One minus 0.155, 2.32 minus 1. So your yield in this case is 0.32 kilograms for every kilogram of feed. So we assume that for every kilogram of feed, this much of yield we will have. Now, since we have already the y, substitute y2. So pasaka siya, pabalik. So now you know the y, you go in here. Okay, to equation 3. So your crystals, which is 0.063 kilograms per second, is equal to the feed times this one, the yield, 0.32 kilograms per kilogram feed, which is correct because you will be producing here the crystals. This one will yield to the crystals. So your feed will have a value of, what's the value of the feed? Can you give me? Okay, I have it here. So for the value of the feed, you have 0.191. So kilogram per second as well. Okay, now you have the feed. You go back to equation 2 for your cooling. Substitute feed to 2. So your Q for cooling, okay, is equal to the feed that we have here, 0.191, okay, kilogram per second. Then we have the CP, 3.2. 3.2 kilojoule per kilogram Kelvin. Then we have the change in temperature. So it's 313 minus 298 Kelvin. Let me check. Daw na memory ako na, but not sure if it's like that. Okay, 313 and 298. So we get to cancel all of this units, giving you a unit of kilowatt. So your Q for cooling in this case is 9.3 kilowatt. Your Q total will be the sum of Q for cooling and Q for crystallization. Your cooling is 9.3 and your Q for crystallization 9.23. Your Q total is 18.53 kilowatt. Okay? So then we go back up to our working equation. So I have now this one checked. Okay, everything is known already, so I substitute to equation 1. So substitute values to equation 1. We have 18.53 U, 140. So this is 140 Oh, we have, class, are you still there? Class?
Yes, miss.
Okay. Okay, nag-low voltage kami. So I thought na-cut ako. So times 10 raised to 3. And I will have here, I converted the kilowatt to watt. It's about to rain here. And we have 140. We have 140 here. UA and the delta T lubmin. 14.43. So you will get the area. The total heat transfer area that is, and that's 9.19 square meter. So if you would be asked for the number of lengths of cylindrical pipes, maybe made of stainless steel, if the material is not known, that would be, your answer should be, how many lengths would you be needing? So you'll be buying around 10 lengths. 80 kung 9 lang imo bakal kulang. So the number of lengths of cylindrical pipe that you will be buying would be 10. Okay, somebody is writing on the chat box, diin diri man sa amin is. Okay, double P lang siya, daw mag-run out. Nga hindi mag-run out, pulbaan ko, basisin ko na cut. Anyway, so this is it class. So this is our answer. The number of lengths of cylindrical pipe. But if the problem is just asking for the length of the Swenson-Walker crystallizer, then it would be this one. But as to how many lengths, that would be then 10. Because if you just buy 9, kulang ka. Okay, you need to have 9.19 square meter of available area. That way, your goal of producing that much of crystals as mentioned in the problem could be achieved. Okay?